Milky Way, we see already that star formation is very inefficient. So in particular, just a very simple exercise, you count how much molecular gas you have in the Milky Way. So then you end up with about 10 to the 9 solar masses. And you can observe that you only form about 1 solar mass per year stars in the Milky Way. And then you can go and check the conditions for molecular clouds in the Milky Way. And from that, we learned that typically the density of molecular gas is between 10 and 100 particles per cubic centimeter, which leads to a free fall time, 1 over square root of rho, which is about 3 to 10 million years, depending on whether we go with 100 or with 10 particles per cubic centimeter. And so that means that the expected star formation rate in the Milky Way, so the time it would take for this molecular gas to collapse into stars, therefore the resulting star formation rate should be of the order of 100 to 300 solar masses per year, and not 1 solar mass per year, which is what we observe. So clearly, star formation is much more inefficient than what we would expect by a factor of 100 to 300. So this is something we cannot ignore, right? And so something else must be going on. And it means that basically the free fall time is not the end of the story. So now the question is, why is star formation so inefficient? Can we understand this with simulations? Then before we move on, we could also say, okay, maybe the Milky Way is just special and the Milky Way is just particularly inefficient in forming stars. So how about looking at other galaxies first? So for that, of course, you probably know the Kennicutt-Schmidt relation, which relates the star formation rate surface density to the gas surface density in galactic disks. And so this is here, the gas surface density is really the surface density of atomic gas plus molecular gas. So basically most of the gas which is available, because only about 10% or so of the mass is in hot gas. So therefore this should really incorporate all the gas which would be available for star formation. And you see here that there's this remarkable correlation between gas surface density and star formation rate surface density over so many orders of magnitudes, more than 4. And if you work out what is basically the relation here between the two, so basically you can work this out as a time scale, how long it takes to convert this available gas into stars. Then again, you come out with about a giga-year, so this kind of very inefficient star formation, which we also see in the Milky Way. And I will just say something about the slope of this relation in the next slide. But from this perspective already, we can really ask ourselves the question, so what's going on here? Does it mean that the star-forming gas is contained in very long-lived clouds, which just hang around for a very long time and don't do anything, and then eventually somehow they collapse into stars? But then the question is, why are they long-lived? As we made the argument before, if they would be gravitationally bound and going into free fall collapse, then we would expect a much shorter depletion time, by at least a factor of 100. Shorter. And the other option would be that, okay, maybe they are partly gravitationally bound and they do form stars efficiently, but then stellar feedback sets in from particularly massive stars, pushing against gravity and therefore stopping star formation locally. But then these clouds would not be long-lived, right? They would be forming rapidly, forming stars rapidly, and then dispersing again. And so basically what you would see is just a net effect of this rapid cycle. And we don't know at the moment what's going on. So just as a motivation for the slope of the Kennicutt-Schmidt relation, there's this dynamical model of star formation, which has been published a long time ago, but picked up also by Krumholtz and McKee in 2005, who came up with an explanation why the star formation might be so inefficient, basically arguing with turbulence in molecular clouds. But so the idea here in general is that you can come up with this type of power law when you relate the star formation rate surface density with the gas surface density times a dynamical rate. So again, this is the idea really that there is somehow star formation proceeding on a dynamical time scale, which if you plug in the free fall time, then you get here some power, some density to the power of minus 0.5. So 1 over that is density to the power of 0.5. And this gives you basically this 1.5 in the slope of the Kennicotte-Schmidt relation. Yeah, again, as I said, this is the idea that, there is collapse going on this dynamical timescale, so free fall timescale. And then what they do is that they patch this with star formation efficiency, where the inefficiency comes in. And so the star formation efficiency, however, is also related to the dynamical timescale. It is a dimensionless quantity, so it's basically dynamical timescale over depletion timescale, where the depletion timescale is very long. But then this drops out of nowhere, basically, that this depletion timescale is so long. So basically, this theory cannot, I mean, it can explain the slope of the Kennicotte-Schmidt relation, but it cannot explain why star formation is so inefficient. So the inefficiency must happen on the small scales in molecular clouds. And now it gets even worse, because if we look, let me skip this, if we look at the molecular star formation law, and there have been a lot of recent studies on this from, for example, the FANGS survey, which can look at the carbon monoxide distribution in nearby galaxies in a lot of detail. Then the following thing has been found. So if you go to the molecular gas, so basically you exchange your x-axis from total gas, which was H1 plus molecular, to just the molecular gas, then all of a sudden your slope is flatter. So you will see a linear relation between the star formation rate, surface density, and the gas surface density. So then you could say, okay, now I basically see a direct relation between what's in molecular gas and what's in star formation. That would be nice, but also if we look at the time scale here for the depletion, then we have a similarly long time scales of a gigayear. So also in this molecular phase, where there's now no more this power of 1.5, still the depletion time scale is very long, right? So basically, this linear relation doesn't resolve our problem that star formation is very inefficient. So what happens in these molecular clouds? Why is star formation so inefficient? And in particular, what I don't understand here, but maybe you guys have an answer for me, what I always ask myself is, so from studies of nearby galaxies in high resolution, but also from simulations, we know that most of the gas, when you go to surface densities above 10 to 50 solar masses per parsec squared, should be in molecular form. So this is this H1, H2 transition, which can be measured. But then, I mean, we know from Kennicotte-Schmidt that the slope is 1.4, and that continues into this regime. So if we go back here, so you see here we have 10 to 50 solar mass per parsec squared is basically here. But also above here we have, at these very high surface densities, we seem to get the slope of power of 1.4. But this gas here should all be molecular, if the H1 to H2 transition would be as we see it in local galaxies. So the question is, how do we get these different slopes together? So because here we have the slope, which is 1.5, but then in the molecular case, we have a slope of 1 roughly. But shouldn't these slopes be equal at high surface densities, where all of the gas should be molecular? So this is a question I have for you later to discuss, if you like. In any case, nothing of this helps us. What we learn is that star formation is inefficient. And so now the question is why? And so, as I said before, so if we go with this free fall time assumption, then we basically assume that the cloud mass is gravitationally bound, because only if it's gravitationally bound, it will undergo free fall collapse. If it's not bound to begin with, it will not undergo free fall collapse. So then there's no problem, right? So the question is it really gravitationally bound? I mean, we know that in reality, we also have magnetic fields, we have thermal pressure, we have shear, turbulence, and so on. But then okay, in some cases it works well that stellar feedback opposes gravity, and I will show such cases. But in other cases, it might actually not work well. In particular, when we go to dense, massive, giant molecular clouds, and it has been argued before that most star formation in the universe happens in very massive GMCs, so more than 10 to the 6 solar masses. So let me show you some examples here. So for these for star formation in very dense molecular clouds with very high surface densities, it's not easy for feedback to stop gravitational collapse once it is proceeding. And you see here different studies. So this is from Howard 2017. I think this was this Nature paper with Ralf Budritz, where they show here the star formation efficiency for clouds with different masses going from 10 to the 4 to 10 to the 6 solar masses as a function of time. So you can see star formation proceeds as a function of time, and it also hasn't stopped yet. In this case, I think they include radiation pressure and maybe also ionizing radiation. But so basically, as you go on, you form more and more stars, and you already reach here 50%, which is way more than the 1 to 2%, which we see on the galactic scales. Similar here, a study by Kim from 2018, where they look at the impact of radiation pressure in stopping gravitational collapse. And here you have, again, the star formation efficiency as a function of surface densities of the clouds. And so you see that for low surface densities, also the star formation efficiency is low. That's fine. Although it's of the order of like 10% for typical clouds, not 1%. But then if you go to higher and higher surface densities, the radiation pressure cannot really stop any longer the gravitational collapse. So also here we go to 60% or so for these high surface density environments. And this is here the study by Mike Rudich from 2018, which also shows a similar thing, reaching very high surface density. Sorry, this was cut off here, the x-axis, but it's also, I think, the surface density. So basically, the radiation pressure in this case helps, but it's not really enough to bring us down to the star formation efficiencies we expect. And in particular now, if we follow this argument that most stars form in these GMCs, so we need to understand why there is such a low star formation efficiency overall, if locally it's not the case. Then there are some models from Rana 2018. These are 1D models with the warp field model, as they call it. And so basically in the 1D model, you also start with a gravitationally bound cloud. You can give it a surface a density distribution in the radial direction. And this alpha here denotes the slope of this density distribution. So we always have a power law distribution, which is peaks in the center and then drops off. And the power law index basically says how quickly it drops off. So basically how concentrated is the density profile. And this density profile with the power law slope of -1.5 is a little bit less concentrated than the one here with -2. So this would be the singular isothermal sphere initial condition, basically. And of course, with 1D, you can do many different models, and you can test the impact of different feedback processes. And so what you see here in the color is actually the star formation efficiency. And so we can see that the slope of this initial density profile has a huge influence on the star formation efficiency, because the color bar doesn't have the same scale. So here it goes, the blue is 6%. So it means that if you go a little bit flatter, you're actually quite inefficiently forming stars. So with just 1% or so, as we expected. But if you go to slightly steeper density profiles and high surface densities, so we want to look at up here, so 100 and above, then again, we get this more than 50% star formation efficiency. Yeah. So same thing here, basically. If you have concentrated, highly gravitationally bound systems, it's impossible to disrupt them by feedback. Now, of course, this is 1D, as I said, and we can ask ourselves the questions, are these clouds, is it really a good assumption? Also enters the freefall theory, basically, that we have spherical clouds which are somehow centrally concentrated. We know, however, that clouds are not spherical objects, but that they are sheet-like, they are filamentary, they have a lot of substructure. And it has been shown in the literature by Samura Vias, but also by us, that in fact, this impacts the boundedness of the cloud quite strongly. I mean, it can actually have a positive as well as a negative effect. So imagine instead of having a uniform sphere, you put a lot of mass into some dense filaments. And then it means also that there's a lot of empty space in between, right? So on the one hand, okay, maybe the gravitational collapse is modified. On the other hand, also once you do have feedback, the feedback can blow out in between the dense filamentary channels and basically get lost and not influence the dense gas very much. So it will hamper also the impact of feedback on the clouds. I think, in fact, what you get in this 1D model is like the maximum impact of feedback which you can possibly get, because there's no way for feedback to escape without doing any work on the gas, right? And it has been shown, for example, by Jim Dale, that if you do have dense filaments and ionizing radiation, the ionizing radiation will just, blow out, and the dense filament is basically, it has such a small surface area compared to the rest of the cloud, so to say. So it's not really experiencing much work from the feedback. Okay, so this was just to set the stage. So now I'm going to speak about how we investigate, therefore, the role of gravity in the clouds, which we are forming in realistic numerical simulations, meaning that we look at molecular clouds which are forming from the multi-phase ISM in galactic disks. And we do this in the SILK project. So what we do here is that we take a piece of a galactic disk and we started with solar neighborhood conditions. We have an elongated box, basically, because we also want to be able to see a little bit the onset of galactic outflows. Of course, there's not a strong outflow for solar neighborhood conditions, so it was never the aim of our project, because sometimes people say with tall boxes you cannot do this. Well, it was never the aim of our project to look at, large-scale galactic outflows. It was rather the idea to get some proper multi-phase ISM developed. We have a lot of physics included. So, of course, we have self-gravity. We also include an external galactic potential, which mimics the old stellar component in the disk. We have ideal magnetohydrodynamics. We have heating and cooling and molecule formation. And this is included in a chemical network, which we are running on the fly. So we form molecular hydrogen and also carbon monoxide on the fly. And then we have radiative transfer in our tree-ray algorithm, which is a backward radiative transfer scheme. And it treats the diffuse radiation from old stars, which are everywhere, which give you some interstellar radiation field, which we usually parameterize with G0. So it's a Harbing unit. And then we have also point sources, which are stars, massive stars. We follow each individual massive star in our simulation. And we follow its wind and ionizing radiation. And at the end of its lifetime, it explodes as a supernova. Once there is a supernova, we also inject cosmic rays. So typically 10% of the supernova energy is assumed to go into cosmic rays. And these are then developed using an anisotropic advection and diffusion scheme. And so now let me show you just one example. So what you see here is a typical simulation. We see here the box from the side view and here from the top view on the bottom row. And so we have here the density as a slice, the gas temperature as a slice. And then we have also cosmic ray energy density as a slice. And here are projections of different chemical species. So here we have ionized hydrogen, atomic hydrogen, molecular hydrogen, and CO. And here we do not overlay the zinc particles, which are star clusters, because otherwise you can't see actually the dense molecular gas. Actually, if you have star cluster zinc particles, the simulation is immediately not anymore ideal to study the molecular gas, because a lot of the cold dense gas is swallowed into the sinks. And so it's no longer present on the grid to do any synthetic observations. So if you want to look at mock observations of CO, you need to do a simulation without sinks, basically, which means you need to go to smaller scales. Otherwise, it's not there anymore. Yeah, so and there's a star cluster population forming. The size of these particles roughly corresponds to the mass in each in the sink particles. So small is like something like 100 solar masses. So this would be only one massive star contained in there, basically. And then here we would have something like 100 massive stars contained in one of these bigger clusters. One is here. Okay. So, and what we can show with these types of simulations is, for example, how the different feedback mechanisms impact the star formation in the overall volume which we simulate, which here it has a size of 500 parsec times 500 parsec and then plus minus 5 kiloparsec. And again, here we show Kennigan-Schmidt relation. So this is star formation rate surface density against total gas surface density, where here we really measure the amount of molecular and atomic hydrogen. We know that from our chemical network. And this is just a simulation where we only had solar neighborhood conditions, so 10 solar masses per square parsec. And it's not fixed at 10 because, as I said, over time, some mass goes also into the hot phase. So we can have a little bit less than 10, but we can never have more than 10 in this simulation. Yeah. And but what we did here was that we switched on and off different feedback processes. So the different so in the background, the gray is observations, and the different points are for different simulations. So each point is a simulation where in this case we only had supernova feedback. So basically we form the sink particles, they accrete, and we sample the massive stars inside. And at each end of a massive star's life, there's a supernova explosion. Then in this case, we also include the ionizing radiation of these massive stars. And here we have supernova and stellar wind. Without ionizing radiation, here we have everything supernova wind and radiation. And in this case, we have supernova wind and cosmic rays. And here we have like everything together, supernova wind, radiation, cosmic rays. And what you can see is that if you have only supernova feedback, your star formation rate is way too high. So you just simply accrete too much mass into sink particles. There's no feedback stopping it initially. So it basically the feedback acts too late in order to regulate the star formation down to the observed level. But if we switch on early feedback, so winds, and in particular ionizing radiation, then we come immediately down to the observed levels of star formation. And then if we also have if we additionally have wind and radiation, then we are here. And if we have cosmic rays, there's a little bit of an impact, but the cosmic rays don't influence the star formation rate so much. Yeah.
Can I just ask a quick question about the simulation?
Yeah.
They look great. So it looks as if you start quietly, and then you have a massive burst of star formation, and then it gets quieter again. I was just asking, is this what you expect of the 200 megayears, or is it because you're not putting in new gas that in a realistic simulation kind of fall in, or so what's
so over that time scale, I would not expect that there's a huge amount of gas falling in. I mean, we do have some gas falling back because it's not all leaving the box. In fact, there's only very little mass leaving the box because we do not drive a very strong wind in this simulation. We don't expect a strong wind for solar neighborhood conditions, right? And so, I mean, there's a little bit of a starburst in the beginning. It depends on how you set up your initial condition to some extent. So what we did here is that we drive some turbulence in the beginning, and then we let the system evolve, right? And what we also tried is that we do some supernova driving in the beginning. But in the end, to have this study here, we wanted to have exactly the same initial conditions for once the star formation proceeds. because otherwise we cannot compare whether it's an influence from the initial condition or from the further evolution. But in principle, we see that there's always some mode of more star formation and then a more quiescent phase. So it's always like a little bit going up and down in time. And it's never in, I mean, we also ran these simulations for a very long time. We never see that we really, you know, do not have these periods any longer. So we always have some periods when we have a little bit of more star formation and then some less star formation. So it's not like we reach this dynamic equilibrium stage, I would say. I mean, it depends, right? If you then average over 100 mega years, you can say maybe there's some equilibrium, but it means that you average out the fluctuation. Yeah. One more question. So all of these feedback processes were not effective in the 1D model. They are not effective for these very high surface density clouds, yes. And we do not. But here they are. They are not. We do not have these very high surface density clouds. Oh, okay. Yeah. So yes, that's a good question. And in fact, this is something we're working on. We have done now simulations also with higher surface densities going up to 100. We find that the ISM is remarkably similar for surface densities between 10 and 100. Basically, yeah, there's of course some more molecular gas and so on, but it's not like it's completely different for 100. So we get I'm not sure I include the plot here, but in fact when we include wind and radiation, we also rely on the Kenny-Schmidt relation with the model here at 100. So, but the thing is that this doesn't. I mean, so the thing is that within the thick particles, we have 100% star formation efficiency here. So what I want to raise is that maybe it's also a matter of how we, define things. Because here we sample over the whole box, which is not a big box. It only has 500 parsec. But if we look in this volume, then we see the correct star formation rate. However, now if we zoom in and we say we look at the scale of our thick particles, so just under 10 parsec, then we would see 100% star formation efficiency in this case, which is not realistic, right? But still, we have to keep in mind this a little bit, that actually it's very important also in the observations to go to higher resolution. And it has been seen in the Fangs observation, they cannot go down to 10 parsec scales, but they can go now to something like 50 parsec scales. And there is this discrepancy that you see higher star formation when you focus on H alpha peaks and lower star formation when you focus on CO peaks. So this kind of scissor-like plot, I don't know whether you've seen it in Truba 2010, for example, where they derive timescales from, this seems to show up. Okay, but here we also don't include radiation pressure yet. So therefore, is another feedback mechanism. But what I wanted to show is that basically this early feedback is very important. So the radiation and the winds are extremely important. And that basically you can, with this, produce star formation rates on the averaged over a couple hundred parsec, which are in agreement with the Kenny-Schmidt relation. So now what I want to do is I want to zoom in. Because in fact, we can zoom in these simulations and study the evolution of individual molecular clouds and the star formation inside in a lot of detail. And I want to address the question, how much of the gas is actually gravitationally bound? And so here we have the scale of the silk box. So this is a couple hundred parsec, 500 parsec. But now what we do is that we know exactly where molecular clouds are about to form. And then we go back in time and we say, okay, this molecular cloud, we will now follow its formation and in detail, and we will allow the code to, adaptively refine the grid as the cloud is forming. And so therefore we can get the filamentary substructures of the cloud and study this in a lot of detail. This goes down to scales of about 0.1 parsec. We also have done some higher resolution runs, but it is not yet at the scale where we actually form massive stars, right? Where we would actually need to go down to less than 10 to the minus 3 parsec, so to have individual cloud. So basically the stars the zinc particles which we form here are still little star clusters. So still, if you go to 0.1 parsec, you have little star clusters. You don't have individual stars, right? Okay, so this is one example for such a simulation. So you can see here the filamentary structures, they collapse to form stars. And then there's ionizing radiation feedback blowing things apart. But you can also see that the ionizing radiation partially affects the cloud. But for example, this dense region here basically doesn't feel anything about the ionizing radiation at first. So it takes a while to disperse the cloud overall. All right, and this is just to show you some, so we can actually do this for different clouds at the same time in the simulation. So if they sit in different regions, this is good for parallelization because then, you know, you can basically run this in the same simulation. Here you have molecular cloud 1 on the top and another one on the bottom. And what I show you here is the chemistry. So here we have the atomic hydrogen distribution, the molecular hydrogen, and the CO. And this is also interesting for people who are looking at molecular cloud observations, because, I mean, in the CO, you really only see the densest part of the cloud. For example, this cloud here looks quite fragmented, right? But in fact, there's a bridge in molecular hydrogen. If you were able to see the molecular hydrogen, which you can't because it's cold gas in this case, then you would see that these structures are connected. And in fact, all of it is enveloped, and also not only enveloped, but the atomic hydrogen is mixed in within the molecular cloud. So although most of the mass might be in molecular gas, there's a lot of atomic hydrogen still hanging around. Sorry.
Are you overestimating the surface density of molecular hydrogen using CO or not?
Overestimating the surface density.
Observations. You said for these each two bridges.
Well, I think the question is rather how much molecular hydrogen do you miss? And we have looked into how much molecular gas is more dark. So we can do the study, and in fact it depends very much on the age of the cloud and the structure of the cloud and whether you have magnetic fields or not. Because when we have magnetized clouds, they tend to have more fluffy envelopes. So then there's more CO dark molecular gas than if you have only hydro simulations, which have steeper gradients on average, and so there's less of this fluffy gas around. But I can show you a plot later if you want. Okay. Then maybe one question about where the molecular gas forms. So this one, sorry. I don't know what happened now. Okay. So the if you wanna estimate where molecular hydrogen forms, you can in equilibrium, you can apply the following rule of thumb. So you would estimate that the time scale on which you turn, thank you, on which you can turn gas into molecular gas would depend on the density of the gas. And so this is a paper by Hollenbach, which is quite old, actually, but it actually holds very well. So the time scale, say you have a parcel of gas with given density n, say, I don't know, 100 particles per cubic centimeter or 1 particle per cubic centimeter, then you could turn all of this gas into molecular gas if you wait 1 gigayear, if you have a number density of 1. Okay, so if you have a number density of 100, well, you wait 1 gigayear over 100. Okay, so 10 megayears. So this is for equilibrium models. So equilibrium basically, if you do not run a chemical network on the fly, but if you were to estimate afterwards how much molecular gas do I have, then you would probably estimate something according to this rule of thumb, because that's the only thing you can do, right? In fact, what you can see here is, okay, we have average densities of 100 or so in these clouds, but our simulation here didn't even run for 100 mega years. Sorry, for 10 mega years. It only ran for a few mega years. In particular, here in the beginning, we have a lot of atomic gas, and then you see it very quickly, the atomic gas drops and the molecular gas is formed in these clouds. So this process takes maybe a mega year or so. Now the question is, for the densities we have, how can molecular gas formation proceed so rapidly? And this is the case because we have turbulent gas here. So basically we have shocked gas, which locally increases the densities, and then there are molecules formed, and then there's a lot of mixing going on due to the turbulence, mixing the molecular gas into the ambient medium, which has lower density. There's also a paper by Simon Glover which discusses this. So I just wanted to show you this because equilibrium models might underestimate how much molecular gas you have, or it might also overestimate it depending on what your conditions are. So if you have a strong shock, it can dissociate all the gas immediately, and then it will take a long time to recover the molecular gas. So therefore, we have this chemical network which we run on the fly. Okay, so now I want to talk a little bit about the substructure of magnetized clouds. And what we do here is that we take these clouds, which we simulated, and we analyze them with a dendrogram. So we do dendrograms in 3D. And so a dendrogram basically, what it does is that you cut at different density levels. So it gives you density thresholds here on the displayed on the y-axis. And then you will find connected structures in space. And these are then structures which are connected in this kind of dendrogram tree. And in this way, so we require at least 30 cells per structure or something like this. So this is a parameter which enters. But other than that, there's not really any parameter. So as a function of density, we get different structures. Yeah. And then we can analyze what these structures look like. And we do this by computing their moment of inertia tensor. And then you can compute the eigenvalues of that and relate them. And this gives you an idea of whether the structure is spheroidal or filamentary or sheet-like. Yeah. And depending on basically whether you have something which is flat or elongated or disc-like or whatever. We also included this here, sheet C, which is a curved sheet. So a sheet which does not contain its own center of mass. And actually we do have some curved sheets. Yeah, so basically it's like a bubble shell, you can imagine like that. And so what we plot here is that as a function of size of our structures, and so this is now the average radius, so to say. We plot how many sheets and filaments and so on we find. And you can see that there are actually a lot of sheets. So our clouds are very sheet-like. This actually does not depend on whether we have magnetic fields or not. It's always the case. And then if you go to some a little bit smaller scales, there are also filaments showing up. But spheroids really only show up at the smallest scales. There are a little bit more, but I mean, they are really not, clouds are not spherical. That's the takeaway message. I can show you some images here for the clouds we all analyzed. So this is what went into this plot, which you've just seen. So these are zoom-ins on different regions. Some are just hydrodynamic. And then we have a lot with magnetic fields. You can see here, actually, this is the total column density, that the runs with magnetic fields, they have more fluffy gas surrounding these dense filamentary structures than in the hydrodynamic case. Yeah, here, I think visually you can already see it. This is all with the same color bar. So, and then I show you here that the clouds are what these sheet-like clouds look like. So they this is basically a 3D visualization of a given density threshold. And then inside, we picked a density threshold where we have more filamentary structures. So basically, these filaments are embedded inside the curved sheets and just in general sheet-like structures. I think they look like flying carpets to me. So they are not actually. So, and we only found them because we had this fun project with our colleagues from the visualization team, we have this cave in Cologne, you know, where you can do 3D visualization. And I always thought this is, you know, just for fun. But in fact, when we did the 3D visualization, we saw for the first time that really there are sheets everywhere. And when you just look at it in projection, you don't see it. Because, I mean, you know, when you project this, okay, you would say, yeah, sure, there are some dense structures and there's some fluff in between, but that these are really like sheet-like structures you don't see. And no matter how you turn it around, it would always look similar to that. But that you really get this, you can only see in 3D. So this was a nice example that you can actually do science with nice visualization as well. Okay, so now let me go to some more plots. I'm not sure how much time I have.
I would say about maybe 10 minutes.
10 minutes, okay, cool. Then let me bore you with some scatter plots for the next 10 minutes. In fact, so I want to now go step by step. So you probably all know alpha vir, which is the virial parameter, yeah? And it typically relates the dynamic, so it relates typically the kinetic energy and the potential energy of the gas. And it tells you something about the dynamic state of the clouds. And if you have high turbulence in the clouds, you have high virial parameter, yeah? So, and what's usually used is this alpha, the standard virial parameter, which really only contains the kinetic energy and the potential energy, because that's also what's accessible to observers in some way. Because usually they cannot see surface terms, they have a hard time seeing magnetic fields, and okay, maybe thermal pressure a little bit, but that's basically the easiest. So that's why they all use it, and it's used mostly. But now we will assess how much this actually tells you about the state of the cloud, and whether it's worth also looking into you know, basically better approximations of the virial state of the cloud. So we will increase the complexity of this parameter as we go on. All right. And we will do this by not only including kinetic energy, but also magnetic energy, thermal energy. And this is now basically the volume term. So what's inside the structure, but also surface terms matter. And we can also compute the surface terms from our analysis. Okay. So now what I plot here is what's typically known as the Larsen relation, but a small modification of it, namely introduced by Heyer et al., where basically Larsen tells you that the 1D velocity dispersion of a given structure, molecular cloud, for example, would scale as the size to the power of 1/2 roughly. And this is what all our ideas that molecular clouds are subject to turbulence is based on. Yeah. Now, what Heyer discovered is that he can reduce the scatter in the Larsen relation when he actually introduces a surface density dependence, and so therefore he plots sigma 1d over r to the 1/2 as a function of surface density. If we were to follow Larsen very strictly, then we would see a flat horizontal line, right? Because if everything would lie on the relation that sigma is proportional to r to the 1/2, we would see this. And Heyer showed that in fact you don't see a flat line, but you see that you have an additional scaling with surface density. And you can introduce here lines which guide the eye for the virial parameter. And what you can see is that basically here we have empty symbols which showcase structures which have less than 50% of their mass in molecular gas. And we have structures with more than 50%. So we call these molecular structures and these atomic structures. Yeah. And so you see that these atomic structures, they do all kinds of stuff. They are very supervirial. But then it seems like as structures go denser, they settle down and then go to higher surface density, going to higher surface density, move up this relation here. And this is the case for hydro as well as for MHD. For MHD, here there are more atomic structures, but that doesn't really mean anything because we have just more clouds in the MHD sample. Okay, we color code here with density threshold, so it means that higher surface density on average also has higher volume density. That's what you can see here. Now, if we look at again this alpha vir as a function of radius for different times, for example, then we can learn several things. So if we go now from left to right, we show 2 different times. So here the cloud is very young, here it is a little bit older. On the top, we have the hydrodynamic case, and here we have the magnetic hydrodynamic case. And here I already made this alpha a little bit more complicated, namely, I include not only the kinetic energy, but also the thermal energy of the magnetic energy terms. Okay, the magnetic, of course, only in the MHD case. Here it is 0. And so what we can see is that there are a lot of structures which are supervirial, so not gravitationally bound. And in particular, they're all with empty symbols. So empty symbol, again, is atomic structure. Okay, most of the gas is in the atomic phase, and only the molecular structures seem to come down to an alpha vir where you say the structure is virialized. All right, and what we can also see from this is that as time proceeds, this picture doesn't really change. So it's not like at later times we see all these structures becoming virialized or more gravitationally bound. What we rather see is that there are more structures which are forming over time. Okay, some of them are then maybe also settling down to become more gravitationally bound, but there are equally more structures here also populating, again, the supervirial regime. So it's just that, so basically what this already gives you the notion that as the cloud forms, the structures are not bound. They form in a fluffy state, supervirialized. And we can look in a minute why they are supervirial. But they are supervirial in the case without magnetic field, as well as in the case with magnetic field. So it cannot only be the magnetic field, right? So also thermal pressure is important. And then over time, maybe they settle down and eventually might become gravitationally unstable. We can summarize this, yeah?
About the last slide, so I'm not an expert in this field, but I was wondering how will observer justify this, because they cannot see molecular hydrogen. Like how will they figure out whether alpha is 1 or no?
So what they do is they look at CO, right, for the molecular gas, and then they estimate well, the CO is a line, so you can see the velocity dispersion in the line, and from that you estimate like the turbulence, and from that you get the kinetic energy estimate.
So the idea is that if they find that alpha is close to 1, then molecular hydrogen is more than 50%. If not, then the other way.
I think they never asked themselves this question. So for them, molecular gas is molecular gas. Yeah. And because they cannot see in 3D anyway, so I mean it's very difficult to disentangle what's going on in the observations. But I can maybe explain you more later. But I have also a few slides where you can see this at on the example of Orion, but I didn't show them today because there's no time. Okay. But so what we see very clear, but basically the ideas, so I mean there have been theory papers which propagate that clouds are, or also this notion that clouds form on the galactic scale via tubular instability or whatever. All of this implies that molecular clouds are gravitationally bound to begin with. And I think what we see is that this is not the case, right? There are many substructures in the same cloud which are not gravitationally bound at all and which contain quite a lot of the mass. And here you can see it very clearly. Again, this is the ratio of magnetic to potential energy and the ratio of magnetic to kinetic energy also. So in particular, also in these atomic structures, these are the red lines. The magnetic energy is also relevant, yeah? And then it becomes less relevant as you go to denser and denser gas. But let me again go here. So this is showing the thermal energy over potential energy. Also here in the atomic structures, the thermal energy is quite high compared to the potential energy, bringing things into the super. So basically thermal and magnetic energy help you to make structures supervirial, in particular when they are not very dense and not strongly molecular. So yeah, exactly. I wanted to show you this. So this is now the alpha Vir as a function of time. And we do not see some sort of evolutionary trend here, right? So so all the atomic structures are always supervirial. Same here in the MHD case. While if you go to the molecular structures, now the blue line, this is for all molecular structures, so all the points which are filled. Also, these are kind of slightly supervirial. Only when you pick out the molecular structures which also have densities, mean densities more than 10 to the 4 particles per cubic centimeter, only then these things become gravitationally bound. Yeah. So we see this, and we see this, that there's no evolution that the cloud overall becomes totally bound as a function of time. This is not the case. So there's some atomic structures which are absolutely not bound. There are some molecular structures which might be bound or maybe not. And then only the dense gas is bound. That's basically what we see. And I think this is the reason why the star formation efficiency is so low. That really only a very small part of the cloud is bound to begin with. So now I'm not sure I have time actually to go through this full Vir analysis, probably not. But you can do this same exercise with now also including the surface terms. And the surface terms are relevant because they contribute sometimes equal share to the volume energy terms. But let me skip this because it actually just gives you the same impression to what we had just now. But I want to show you this because this is basically the takeaway message. So what we did here was that we plotted now the size of the largest bound structure in our cloud as a function of time. And this is for the different clouds we simulated, which I showed you in the beginning. So we have these two hydrodynamic clouds. These are the red points. And we have the MHD clouds here, which are the so bluish points. And so this is the size of the largest bound structure we find in any of these clouds. And the red band shows you the largest, the cloud size, basically. And so we can see that for some clouds, there are some bound structures which actually are really also sitting on the largest scale or slightly below that. But then there are many clouds which have only bound structures as much smaller scales. Yeah. So I think that's important. So it shows again that not the whole cloud is gravitationally bound, but only small scale structures inside these clouds are bound. And so these are potentially bound structures where you can also say something which is definitely bound based on the surface term analysis. And here, basically, you go to tiny scales for being sure that something is gravitationally bound. And the same is true for the mass. So if we just look at the mass of the structures where we are sure they are gravitationally bound, then for some clouds, this is such a low percentage that we can't even plot it. And okay, there are 1 or 2 where maybe we go to 50%, but only for a short period of time. But on average, we have maybe here 10% or so of the mass, which is definitely bound. Yeah. And so this is actually what I wanted to conclude with. So basically what our Vir analysis shows is that the magnetic field and the thermal pressure have a strong impact on the atomic gas phase, which is mixed inside the molecular clouds. So you cannot really you cannot say the mass in a molecular cloud is only molecular mass, but there's a mixture of atomic and molecular gas. And if we, split it up into substructures, then in particular, the atomic gas is supported by magnetic and thermal pressure. And the atomic gas within molecular clouds is certainly unbound. And so is actually also the average molecular structure. Only when you go to the dense molecular structures, then these are gravitationally bound. And so therefore, we can work out that only a third of the clouds which we simulated have something like 50% of their mass in potentially bound structures. but basically it means that 2/3 have very, very little mass in bound structures. So most of the cloud is not gravitationally bound, right? And so the surface density dependence, which is in the higher relation, also just starts to appear for these self-gravitating objects. And I think this brings us to the conclusion that if we look in detail, we see that clouds are not gravitationally bound, but I think we need to rethink then how this, theory, which is based on gravity on the large scale, can anyway go together with the fact that clouds are really not bound on the small scales. And I think this is something we need to work on in the future. And for that, I have a open questions slide. So basically, as I said, we can show that most of the cloud mass is not bound. Now the question is how we apply this to denser environments and more massive clouds. Does this basically the scale of the largest bound structure, does this grow to larger scales as we go to more massive clouds? That's something we want to investigate. And also how to connect to observations, because as we just said, the terms are often not accessible. And I think here the computational challenges kick in because we really need the resolution. So we need this high resolution in order to see all this substructure. We also need accuracy in physics and statistics because you saw that every cloud is different, right? And so I think this is something which will keep us busy for a little bit longer now. All right, so thanks and happy to take questions.
So thanks for nice talks. I'm not in the field, so this question might be basic, but you said at the beginning that the storyline of sublimation being very inefficient, and then you simulate the volume which is similar to like solar conditions. I was wondering, the Milky Way has a bunch of different structures, right? So is the star formation rate, does this occur in an environment that is similar to the sun, or is there like a plethora of different environments, and essentially we have to look at all of these?
Yeah, there are many different environments, and we need to look at all of these. That's correct. And in fact, yeah, I mean, so right now we are investigating how to do the zoom-ins in the dense environments, because here it was easy to do because we could basically track down individual clouds, like clouds in the solar neighborhood, like Taurus or Perseus or whatever. So okay, it's gonna form here in 10 million years, so we can zoom in now, But in these high surface density environments, you see like a network of molecular gas everywhere. And it's impossible to pin down some cloud which is going to form at some point. The reason why we don't want to zoom in once the cloud is already there is that molecular gas likes to self-shield. And once you have it, it's very difficult to get rid of it. This is point number one. And point number two is that when we played a lot with the zoom in stuff, and when you zoom in too late, when the gas already wants to be dense and molecular, then you dissipate too much of your compressive turbulent modes, and you end up with rotating blobby structures, which don't look like the molecular clouds we see at all. So you lose the filaments basically when you zoom in too late. And so therefore we are working on this right now. It's really a challenge. We don't know computationally how to do it right now, to be honest. Yeah, that's why we haven't looked at these very massive clouds, because it's just super difficult to do it. Yeah.
Hi, thanks for a nice talk. Okay, I have one question, let's say now. And it's on this last interpretation based on the Dirac parameter. So I wonder if at high densities where you see that basically they're all of this, they're all basically on the alpha equals 1 line. If how this helps you understanding why the efficiency is low also at high densities, and
you mean this plot?
Yeah. Well, on the one on the left more. Like at high density, they're basically all on the alpha 1.
Right here.
And so you would expect them to be virialized.
Yeah.
To them, or soft virial, I don't know if I see correctly. And my question is, can I interpret this in a way that, like the structure that you see, for example, filaments and sheets at high density are so much well-defined and at low densities, and this is the reason why you have low efficiency and not the favorite parameter? Or
so I mean, I think these I mean, at some point you want to form some stars, right? So I think that eventually these dense structures will be the ones which collapse and form stars. So it's okay to have you know, star formation at some point. You don't need to support everything. You just need to support most of the mass of the cloud. So what I'm saying is that not so that the mass which is contained in these structures, this is maybe 10% or so of the total cloud mass. Yeah, and so eventually then these will undergo gravitational collapse, which is fine. But you know, most of the cloud mass is actually not gravitationally bound. Do you know what I mean?
but at high densities, there seems to be all gravitationally bound.
Yeah, but it's okay. But this part is what makes up this 10% mass fraction of gravitationally bound structures.
Yeah, maybe a question I have that would help to clarify. So in these simulations, you have also sync particles, right? So if
No.
so this is without sync
Yeah.
particles. Okay, then this doesn't clarify.
Yeah. Yeah, we did this analysis
Yeah.
on purpose without things, because otherwise you can't do it. Yeah.
Maybe a quick question. What is like initially you were motivating about the star formation rate is inefficient. Then you showed 1D simulation in which if you choose a -1.5 density profile, then you were able to produce the like percent level star formation rate.
Sorry, say again.
So like initially slides you were showing some 1D simulation in which you choose the slope as -1.5, then you were able
Yeah, the warp field model, you mean? Yeah. This one.
Yeah. So maybe I missed after this, but why this thing doesn't solve the issue, like the initial issue that we are not able to, the star formation rate is very inefficient?
I mean, this is for yeah, this is a 1D model, so we have to, you know, we have to check out what it's really like in 3D.
Okay. So,
and I mean, nobody would tell you that a cloud should be -1.5 and not -2 or -1 or flat or whatever. So I think we need to investigate in the 3D simulations what's actually happening.
okay.
Yeah.
I was thinking if we are finding this particular star formation rate, then maybe this is a...
Because I mean, this is a valid question, what you're asking, but what you would be asking is then why do clouds have a flat profile basically, and why are they not more like singular isothermal spheres, which some people like too, but yeah.
Yeah, so I have this picture in my head, which may be incorrect, of these crisscrossing shocks sweeping up all this molecular gas that then is unbound, and some of it happens to be bound. Is that kind of what's going on, or?
Yeah.
Because it's not gravitational, as you said.
Yeah.
Most of the gas is not being concentrated by gravity.
I skipped this before, but in fact, when we include the surface terms, we can show that the ram pressure is sweeping up the gas and holding it together. And in fact, when we look in more detail, we can see that typically filamentary structures are formed by ram pressure compression. Then there are some which are formed and held together by the magnetic surface term. But this is only in more quiescent environments where there are not so many shocks. So if you have more shocks from the background, then it's really the ram pressure which is sweeping up stuff. Yeah, so that's right. But we can show this now, actually.
Yeah.
So that's nice. Yeah.
So I have a question. So if you go to the higher density environment, in particular, if you go to higher redshifts, right? As you know, there are these things. Okay, maybe star formation efficiency is much higher for those objects. How does this fit into this picture where, according to the model you showed, right, you would assume they're still on the alpha equal 1 line, and so essentially the star formation efficiency wasn't actually that much higher, right? So is there any kind of transition? Is there any change that's going to happen because of maybe the physical conditions, or say the feedback is not affected.
So I do think that a change happens when I mean there must be some change happening in the feedback when you become optically thick towards infrared radiation. So that's when the radiation pressure becomes efficient. But then also, I mean, yeah, I mean you're with higher surface density, you're probably more gravitationally bound. But I'm not sure actually I get the question, to be honest.
Well, the thing is that the efficiency is more like 100% or 50%.
Oh, we don't know,
it's
right?
not like 1%.
Yeah.
No, it's based on the, well, we don't know for sure, but it's based on the high star formation rates we see in some of these objects. And so the question is, what's going on there? I mean, for some reason, it appears that the feedback or the sloshing or whatever it is, it needs to be less efficient. I was wondering whether you had some thought about this. Or
yeah, but I mean, in fact, I mean, this is what these models show, that if you have these very massive clouds, then and if they are gravitationally bound on a large scale, then the feedback has a very hard time stopping star formation.
Okay.
Yeah.
This is also for more or less quiescent disk, right? Not a lot of mergers going on.
well, the model is very general. In principle,
But I mean, the conclusions from simulations, assuming.
You mean the highest? You mean the conclusion that the star formation efficiency is low, or the conclusion that
Well,
I don't know.
yeah, I was just trying to.
I mean, but I'm not sure exactly what you mean, because if we look, I mean, if we look at Kenniker-Schmidt,
right? With the
yes,
right.
exactly. But so then, of course, it seems that these are more efficient.
Right, but you had the plot where you showed the Leroy stuff on top, right? And you no, not this one.
Oh.
It's later.
Ah, right. You mean this one?
This one, right? And it seems, I mean, okay, it's hard to know exactly what's going on, right? So the question is, will your models at some point, will they keep following this line?
Yeah,
At some point,
I
they
should have
above it?
I should have included this. Our models lie on this line. I should have included this plot. Maybe I have it somewhere. Right. I have so many slides in this talk, but not this one. I can show you later.
Yeah,
But it's in the paper from Tim Ratian from 2023. Yeah, we have the plot with the different surface densities. Yeah, and so we go up to 100 in this case, and there we have we are basically where the blue point is now. So we have somehow here. Although of course this is only the label. Yeah, that would be the simulation. Yeah. So, but I mean, okay, I mean for these SMGs, you see that you know there's an offset in this direction, so it means that the depletion time goes down, but it doesn't go down to 1 million years or so. It goes down to, I don't know, something like 100 million years, I suppose. Yeah. So I mean, on average, it seems that star formation is a little bit more efficient, but I don't think, I mean, if it were 100%, it would be the point would be way off. So I'm not.
well, it's more like maybe 100%.
So I think that there might be some bias when we look at high redshift galaxies, because we have a temporal variation in the star formation rate. It could be that we see the brightest objects which are in a starburst basically, but that this is not maintained over a long time. That's what I think would explain this behavior, this what we see there. Yeah.
Thank you. Any more questions? Okay. Yeah.
Super quick. As a very briefly mentioned that as a conclusion, I guess, that to be star formation, you need to be both molecular and high density. Right?
Mm-hmm.
So which one is more crucial in different density?
High density. The molecular doesn't actually matter too much, because molecular line cooling is negligible compared to dust cooling for high density gas.
But so how do I explain the high star formation rate? Dots, for example.
Sorry, I'm not sure I understand this question. What do you want to?
How do you get the high star formation rate, density points? I mean, those are the data points.
Yeah.
Very high star formation rate.
You mean this?
Yeah.
Well, I think that this probably is some local temporal variation, to be honest. So what we this data from Leroy is already it's not so well resolved as the FANGS data now, but it's also not averaged over the whole galaxy any longer. So there are some patches which are undergoing some period of higher star formation and some patches of some period of lower star formation. So there is some variation, and also you can see this here in our plot, basically, that there is this error bar which comes from sampling 10 mega-year bins of star formation in our simulations. So there is quite a temporal variation going on. And in the observation, you of course cannot follow this in real time because the period of star formation takes several million years. So therefore you see what you see, and you might also see some of the objects which have high star formation at the moment. And I think that probably these points here are for more towards the centers of galaxies, where our model is also not particularly applicable, because in the centers of galaxies you need to include the galactic environment, right? There can be some bar. There are strong effects from the galactic environment which need to be considered.
Okay, good. We still have probably 2 seats available, I think. No, we have no more seats available. Okay, let's thanks for checking in. All right, so when are we going? At 12:30?